Okay, so today we're going to bring up a new concept, and it's going to be called impulse. So if you remember from last class, we talked about momentum. And the formula for momentum is that one there. I'm just going to write it on the board over here too. Momentum is this little p, and it's equal to mass times velocity. And we also talked about rewriting Newton's second law, which he talked about earlier, as a net force acting on an object is equal to the change in momentum over change in time. So now we're going to introduce impulse. So what impulse is the change in momentum of an object. So you find it by multiplying the net force times the time. So I'm also going to write that up on the board. So it's kind of confusing because the symbol is similar to momentum, but now we have the little triangle. So the change in momentum, that's the impulse, is equal to the force times the change in time. Are you still with me? If you're following on the notes, that would be a new topic, and you can copy down the formula, but I have it on the board. Another way we can write impulse is if we take the formula that we have for momentum, mass times velocity, and we input it into the impulse formula. So our little change in momentum here, we can rewrite that as just the change in the mass times the velocity. And if our mass is the same, then it'll just be the mass times the change in velocity. So we can also add that to our formula sheet. So this whole formula here, that is impulse. A couple other notes on impulse. It's a vector quantity. So does anybody remember what a vector quantity is?
Both force and direction.
Yeah, so it has a magnitude and a direction. So like if I had a positive momentum and I experienced a positive impulse, how would my momentum change? So positive momentum, and then I experienced a positive change in momentum.
Speed up?
Yeah, so my momentum would get greater. Okay, so now I'm gonna work through a couple examples with you, and we'll see. It can be a little bit confusing, but we'll try and kind of get a handle on it. So here we have two cars A and car B. They have the exact same mass, and they're traveling down a road at the exact same speed. They both hit the brakes at the same time, but car A takes 4 seconds to stop, and car B takes 8 seconds to stop. So let's think about this for a sec and think about which car or how the impulse between each car differs. Does car A have a greater impulse, car B, or is the impulse the same? So let's look at our formula here, and I'll just take a second to think about it. And when you've come up with an answer, I want you to just raise the finger 1, 2, or 3 that corresponds to the answer on the PowerPoint. Anybody have any ideas?
Is it A?
No, we just put up your hands and we'll go through it. We'll go through it later. So you think it's A. Does anybody?
Oh,
so you also think it? Okay, so everybody thinks. Oh, so we have a couple A's and a couple B, but nobody thinks they have the same impulse.
No.
Okay, I have a shocker for you.
Oh no.
They have the same impulse. And I'll explain why. So remember, we have our formula here that impulse is equal to mass times change in velocity. So if we go back to our example with the cars, they have the same mass, they have the same initial velocity, and they have the same final velocity. So it takes them a different amount of times to slow down, but the impulse is the same because the change in velocity is the same.
Mm-hmm.
So let's take the same two cars, and now let's think about the forces that are acting on the cars. So we've already agreed that they have the same impulse acting on them, but I'll give you a hint. They have different forces, so it's not option 3. So let's use this formula again, and we can decide which car do you think has a bigger force acting on it.
We're doing fingers again.
Fingers again. Yeah. So we got some ones and a couple twos. So the answer is car A.
Yes.
So the big difference that we're given in the question is that the change in time is different for them, right? And the impulse is the same. So if the time increases, as it does for car B, the force is going to have to go down in order to keep the impulse the same. Is that making sense for everybody? Okay. That's just the explanation. Okay, so now we know impulse is kind of a force times a time, and it's the change in momentum of an object. Can you think of any practical applications where that could be useful? How about our last lesson on cars?
Airbags?
Yeah, airbags. So in a car crash, we're going to talk about it later, but in a car crash, you have a force acting over a time. So if you can increase the time of the car crash, the force is going to go down. Another place it happens a lot is in sports. Does anybody want to take a guess where this might happen in sports?
A mouth guard?
A mouth guard would be the same thing. It would slow the teeth. But more so, think about a hockey player shooting a puck. He's exerting a force on the puck, and he's exerting it for a certain amount of time. So if he exerts his force for a greater amount of time, what's going to happen to the speed of the puck?
It's going to be faster.
It's going to be faster. So that's where you always hear about stuff like in hockey or even boxing, golf, baseball, when coaches talk about the follow-through. It's about you want to follow through on your shot or follow through on, if you're boxing, it'd be a punch, because it increases the amount of time you're interacting with the object. That's going to increase your impulse and it's going to increase your speed. You also see it with a bow, it'd be the same thing. The longer you pull a bow, the more time the force is acting and the faster your arrow is going to go. Okay, so now we'll do a worked example. This is kind of similar to what we talked about earlier. So now we have a car. The car has a mass. Its mass is 1,500 kilograms. Sorry, my writing's kind of tiny. And it crashes straight into a light post. It's a very strong light post. It doesn't fall over. The car just kind of stops. So the car takes, our change in time is 0.05 seconds. And the car was initially traveling at 50 kilometers an hour. So, what's the impulse on the car? Which formula do you think I'm going to use? What do we have? We have mass, we have speed, and we have time. So which one of these two, I'm going to choose one of these two. Which one do you think I'm going to choose? This one? Yeah. So we'll do the mass times the change in velocity, and that's going to give us our impulse. So our mass, that was 1,500. And our change in velocity, it would be velocity final minus velocity initial. So that would be negative 50. And that's going to equal our impulse. So if we do the calculation, the impulse on the car is negative 7,500 newtons. And then using the impulse, we can put it into our other formula, and we can find the net force acting on the car. So if we take our formula for impulse is equal to force net times change in time, we can just input or take the time over here and do negative 7,500 newtons times our change in time up here, which is 0.05 seconds. And that is going to give us a really big number. It's negative 150,000 newtons. So that's how much force the driver of the car would be getting when he crashed into this light post going at that speed. Which doesn't seem like a lot because he's only going 50k an hour, and it seems like a really big force. And that's not quite a real scenario, so how can we reduce the force acting on the car? We kind of talked about this a little bit earlier. If we want the force to be less, what of this can we change? Assuming it's going the same speed.
The mass.
The mass, okay. We could change the mass.
Kick out the back.
So let's assume the mass and velocity are the same. So as we talked about it, so the impulse is going to be the same. What can we change if we want less force on the car? We can extend the time of the car crash. So the amount of time it takes the car to slow down. So instead of just hitting the light post and coming to a stop bang, we're going to try and kind of cushion the crash of the car. So how they do that in cars, oops, that's wrong. How they do that in cars these days is, the slide is missing.
Oh, no.
Okay, anyway, they do it with what they call crumples. Oh, here it is. It's not missing. That's good. So they got things called crumple zones. So on the front and usually the back of the car, there's an area made out of a softer material that will actually crumple when it crashes. And when it crumples, it kind of acts like a cushion or a spring, and it slows down how fast the car stops so that less force gets transferred to the driver. Other things, you have seat belts and airbags, which also they work to slow down how fast the deceleration of the driver is. So if we do the same calculation we did before, but now it takes the car 0.25 seconds to stop. So all we're changing here, our impulse will be the same. I'll just kind of erase that. So our impulse is the same. It's going to be that 75 or negative 7,500 newtons. But now our delta T up here is going to change, so it's 0.25 seconds. So we'll just go through that same calculation again. So our impulse times our change in time, and it's going to give us our force net. So negative 7,500 newtons here, and then times our change in time, which is 0.25 seconds. That will give us a net force of only 30,000 newtons.
Should that be division?
This?
Yeah.
Yes. Someone's on the ball.
I would have never thought
Still no
that.
idea she was.
Did I do it as multiplication the first time too?
Yeah,
Okay.
yeah. I was like,
Anyway, so now you can see our force is 30,000 newtons. So that's like 5 times less than it was before. So just using that crumple zone to kind of slow down the speed of the car allowed us to decrease the force on the driver by 5 times. So that's kind of the same thing you'll see with helmets and stuff on if you're playing football or on a bike. What you're trying to do is you're trying to slow down how fast whoever's falling is stopping, and that decreases the force. Just to kind of illustrate the concept, we have a quick video here of how a crumple zone actually works, if it loads. Okay, it doesn't load. Basically, it's a video of a car crashing. But that's all for today.